Welcome to iLecture Online, and here's a very special type of direct current circuit. It does have resistors in parallel and in series, but it has multiple battery sources on multiple branches. And this becomes a very complicated type of problem that in our conventional way of solving circuit problems, you probably couldn't solve this one. So we're going to use something called Kirchhoff's rules, and we'll go over that in just a moment, to solve the problem where you're supposed to find the current in each of the branches. Now, to get you a little bit more familiar with the terminology, this place right here where circuits come together is called a branch point. So there's one branch point, let me label it as point A, and here's another branch point, let's call it point B. And so there are three circuits running between A and B. You can go from A to B this way, you can go from A to B this way, you can go from A to B this way. So there are three different ways in which you can go from A to B, and therefore there are three branches. And we're supposed to find the current in each of the three branches. So what you want to do then is you want to assume you know which direction the current will go. So since this is the positive end of this battery, and that's the positive end of this battery, you can probably assume that current will flow this way in this branch, so let's call that I1. You can assume that current will flow in this direction in this branch, so we'll call that I2, and then presumably current will flow this way in this third branch, call that I3. Now, let's say you're not sure, that doesn't really matter. You can draw the arrows in the wrong direction, and then the corresponding answer you'll get will be negative, which means that, oh, you should have drawn the arrow in the opposite direction. So a negative answer with the wrong direction current arrow will still give you the right answer, so you don't need to worry about that. You can guess wrong. So first you put down the assumed direction of the currents. Now you need some way of finding what those three currents are. And we're going to therefore use the Kirchhoff's rules. Rule number one says that any currents entering a current branch, for example right here, so all the currents entering branch A should equal all the currents leaving branch A, which is kind of like looking at like an intersection in the city. If you count all the cars entering the intersection and you count all the cars leaving the intersection, usually the number of cars you'll count will be the same. Same with the currents. Current can just disappear. It enters the branch and it leaves the branch. The amount of current entering the branch must equal the current leaving the branch. So what we can say here is that the currents entering branch A, which is I1 plus I2, must equal the current leaving the branch, which is I3. And this gives you the first equation you need to solve this problem. Now notice there are three unknowns, I1, I2, and I3, which means you're going to need three equations to solve this problem, and this is only one of the three equations. The other two equations you get by using Kirchhoff's second rule, which says that if you add up all the voltages going around in a circle, so if you go to a circuit, you start from some point right there, and you go all the way around a circuit, and you get back to the same point that you started with, and you add up all the voltage rises and all the voltage drops, they should add up to zero. So what he's saying is that the sum of all the voltages around any circuit should always add up to zero. Okay, using that principle of Kirchhoff's second rule, we're going to go around this loop right here. So let's call this loop 1, and let's call this loop 2, and we're going to go around each loop in a clockwise direction. Starting from A, I'm going to cross this resistor right here, and I'm going to cross the resistor with the current. If you travel across a resistor with the current, you have a voltage drop there. So the voltage drop there would be I times R, so it would be 6 times I3. So that's the voltage drop across this resistor since you're moving with the current. You come around the corner, now you go across this resistor, and again you're going with the current, but in this branch it's current I1, so the voltage drop there would be, since it's a voltage drop, I need to call it negative, right? It's a voltage drop, so minus the voltage drop here, which is the resistance 4 times the current I1. Then I come across here to this battery, I go from the negative end of the battery to the positive end of the battery, so going from here to here, I have a voltage rise of 10 volts, so that's plus 10 volts. And then finally going across this resistor, again I go with the current, so it's a voltage drop. It's this resistance times this current, so minus 2I1. And then I get back to A, so all those voltage rise and drops should add up to 0. And there's my second equation. So this is from loop number 1. Loop number 2, I can do the same thing. Starting from A, I'm going to go around the loop. I'm going to go around the loop in a clockwise direction. It's arbitrary, but I just chose clockwise. I go across this battery from the plus to the minus end of the battery. So this is a voltage drop of 15 volts. So minus 15 volts. Then I come to this resistor. I go across the resistor against the current, which means that the voltage rise. So this would be a plus 8 times I2, plus the resistance 8 times the current I2. Then I come around the corner here from B back to A. I go across this resistor against the current. So that's again a voltage rise. So that would be plus 6I3 and back to where I started from. So all those should add up to 0 as well. So that's the equation I get from going around loop number 2. So I use Kirchhoff's rule number 1. Sum of all the currents entering a branch equal to sum of all the currents leaving the branch. And then I use rule number 2 twice around 2 loops. The sum of all the voltage rises and drops around any loop should add up to 0. I do that twice, and now I have 3 equations and 3 unknowns, and I'm now ready to solve for the currents. Before I do that, I may want to simplify things just a little bit. I have I1 here, I1 there. You may want to bring those together, add them together, but not necessary. We can probably do without it. But what I'm going to do now is I'm going to use this equation right here, the equation I used from saying that all the currents entering a branch must equal all the currents leaving the branch. Since it's already solved for one of my variables, I3, I can substitute that into my second equation right here for I3, and I can substitute that into my third equation right here for I3. If I do that, I will eliminate the variable I3, and then I'll end up with 2 equations with just 2 unknowns. So let's do that. So these 2 equations right here now will become the following 2 equations. Minus 6 times, instead of I3, I write I1 plus I2. I1 plus I2. Minus 4 I1 plus 10 minus 2 I1 equal 0. The second equation, minus 15, and I don't have to write volts. That just gets things a little too complicated here. So just simply minus 15, because we know that everything is in terms of volts, plus 8 I2, plus 6 times I3, and I3 is I1 plus I2, so I write I1 plus I2, and add all that together, I get 0. All right, now, notice that these equations only have an I1 and I2 in them. Now we combine like terms. So I have a minus 6I1, minus 4I1, that's minus 10I1, minus 2I1, that's minus 12I1. So I take these 2 equations and I rewrite them right here. I get minus 12I1. Then I have a minus 6I2. There's only one of those, so minus 6I2. And then I have a plus 10 on the left, which I'm going to move to the right, and that becomes a minus 10. So I've taken this equation right here, simplified it by adding all the I1 terms together, minus 6, minus 4, minus 2, that's minus 12. All the I2 terms, there's only one right here, minus 6 times I2 is a minus 6I2. And then I took the constant, which is on the left side of the equation, moved to the right, and became a, equals, I forgot my equal sign, equals minus 10. All right, now for the second equation, I have a 6I1. Then I have an 8I2 plus 6I2, which is plus 14I2. And then the minus 15 on the left side, the constant I move to the right side, it becomes a plus 15. There you go. And there's my 2 equations from my 2 loops that are now in a very simplified form. I can now solve those 2 equations for one of the 2 variables. And probably what I want to do is multiply the second one by 2, because then this will become 12I1. I can add the I1s together and they will drop out. So I'm going to multiply the second one times 2. So repeating 2 equations, I get minus 12I1 minus 6I2 equals minus 10. And then the second equation then becomes, when I multiply both sides by 2, I get 12I1 plus 28I2 equals 30. So multiply the second equation by 2. I can now add the 2 equations. The I1s drop out. Plus 28 minus 6 is 22I2 equals plus 30 minus 10 is plus 20. Then divide both sides by 22. And I get I2 is equal to, and then with a calculator, we get 20 divided by 22 equals 0.909, 0.909, and of course we know that's going to be in amps because we're looking for current here, and I found my first of the three currents, I2. Now I need to find I1 and I3. I can go back to one of my two equations, for example this one right here, and solve for I1 in terms of I2. So I'm going to take this equation right here and say I have 6I1 plus 14I2 is equal to 15. Solving this for I1, moving the I2 across, I get 6I1 is equal to 15 minus 14I2. And then I plug in I2, what I2 is equal to from this equation right there. So now I have 6I1 is equal to 15 minus 14 times 0.909 amps. I don't need the amps, I'll just leave the amps off for now. Keep it a little cleaner. There we go. So multiply times 14. Subtract that from 15. And I get 2.27. So 6I is equal to 2.273. And then of course I divide both sides by 6. And I get I1 is equal to, divided by 6 equals 0.379 amps. So now I have found my second current. I found I1 and I2. Then I use my first equation here where I can solve for I3. I know that I3 is equal to I1 plus I2, which means it's equal to 0.379 amps plus 0.909 amps. So when I add those together, I get 1.288 amps, I3. And let's quickly see that's correct. That's 1.2, 1.27, 1.288, and that is correct. So I have my three currents in my three branches. And notice that all three of them came out to be positive, which means that my initial assumption of the directions of the three currents was correct. And that's how you do that. Now, quickly summarizing, because this is kind of a complicated problem. You get a circuit like that with multiple branches, multiple loops, and multiple voltage sources. So the best way to solve that is by using Kirchhoff's rules. There are two rules. The rule number one says that all currents entering a branch equal all the currents leaving the branch. There are two branches here, two branch points. So you can use either A or B, doesn't matter. We used A. We had two currents entering the branch equals the current leaving the branch. I1 and I2 entering, I3 leaving. There's your first equation. Then you use the second rule of Kirchhoff, where he said that the sum of all the voltages across around any loop always add up to 0. So we had two loops right here. We went around each loop in a clockwise direction, starting from branch point A. And so you sum up all the voltage drops and all the voltage rises, adding up to 0. You do that for the second loop. And then you end up with three equations and three unknowns that you must solve algebraically to come up with the three currents. And the preferred method probably is to take the first equation, solve it for one of the variables in terms of the other two, and substitute into the two other equations, which I did here. And that's probably the easiest way to do that. So that's how you use Kirchhoff's rules in this kind of circuit.